astronomy. We're in for a treat tonight. I mean, how much do we really think about Venus being about the same size as the Earth? Various landers landed on Venus in the 1970s. And as I recall, the longest survival of any lander was about just under an hour and a half. It's a pretty deadly place to be. It's dangerous, it's hot, it's high pressure, it's chemically active, and wants to deteriorate your spacecraft. So we have an expert on Venus, Dr. Susan Smrekar from JPL, who is the real thing, a Rocky Planet Geoscientist with a PhD in geophysics from SMNU. And you see all the awards she's received, but she studies Venus. And now the thesis here is as we all know, it's supremely uninhabitable, but it might have been the first planet with habitable conditions. And so there's a lot to learn from the evolution of this planet and its implications for life elsewhere. So I will please welcome Dr. Sue, and I will turn the presentation over to you.
Excellent. Okay. Well, this is some artwork that we commissioned. It is representative of data from the surface of Venus. What you see there is a trench in the foreground. We believe it's a subduction zone, and that there is active volcanism in that area. But I'll talk more about this type of feature as I go through. So next, please. Yeah, so this is going to be a very different presentation, primarily focused on the geoscience. But since I am speaking to an astronomy club, I thought I would start with a little bit of astronomy. Yeah, great. Yeah, you can go on to the next slide, please. So I'm sure you all know Venus is the perfect. The third brightest object in the solar system, and it's been super important in past mythology as well as in the history of early astronomy. So in Roman Greek mythology, of course, Venus is goddess of love and all that, but in Mayan culture, Venus is the god of war, so always slaying the sun. Next, please. There's great detailed records of Venus's trajectory through the skies from both the Babylonians and from the Mayans. The tablet on the right is about 7th century and describes Venus's appearance in the same place in the sky every 8 years. And on the right is a very detailed tracking of Venus by the Mayans, and nothing happened in Mayan culture unless you were paying attention to where Venus was. There was no going to war, no planting the crop. Everything was based on where Venus was in the sky. And going on next, please, to the age of telescope. Venus was very prominent in early astronomy experiments, particularly the transits of Venus were very informative. Lomonosov was able to discover that Venus had a thick atmosphere using the first transit, or the first one of the very early recorded transits of Venus. And if you go to the next page, please, that were made that showed how the atmosphere of Venus approached the sun and transited in front of it. It appeared to, blend with the sun as that was a very key discovery made early in astronomy history. If you go to the next one, please. Edmund Halley was predicting the use of the next. He actually didn't live to see the next transit of Venus, but he used he predicted when it would occur and advocated for determining the distance between Earth and the Sun, the astronomical unit, by measuring the position of Venus with respect to the Sun from different locations on the Earth. So we have Venus to thank for the original astronomical unit determined. Yeah, so this just lays out the map of the various transits of Venus. I hope you saw and including their tree over time. Are you seeing a black slide? It's a little bit delayed on my end as to when I see what you're seeing, but it should be slide number 8. Oh, there we go. Okay, great. So this shows, how the various transits have been used over time. And I hope you saw the most recent one in 2012. People were observing it sort of as practice to see what it can be learned from exoplanet transits. And I hope you saw the next one is over 100 years away. So, and yeah, next, please. So now I'll talk about Venus in the context of exoplanets. And if we go on to the next slide, you probably know that Venus and Earth are practically twins. It's just about 5% smaller, has a similar bulk composition. And it probably once had an ocean's worth of water, at least a shallow ocean, based on isotopic data. And as I'll talk about in a bit, if you go to the next slide, please, the one with the green planets. We see Venus is on the left, Earth in the middle, and an imaginary exoplanet on the right. So Venus has a very young surface. It's hard to compare directly ages with the Earth, given all the erosion and so forth and the oceans, but it has a surface age on average less than 500 million years, or around 500 million years or less. And the age of the seafloor on Earth is up to about 200 million years old. The continents are, of course, older, but are constantly being eroded at the surface. Of course, it's the evil twin, Earth's evil twin, because of its noxious atmosphere of 460 degrees Celsius, or about 900 Fahrenheit, 90 bars, 90 times higher pressure than the surface of the Earth. So the massive carbon dioxide atmosphere is where the original runaway greenhouse was to make the CO2 act as a supercritical fluid. So properties of both a fluid and a gas. And interestingly, it has no magnetic field. However, despite the hundreds of exoplanets being discovered around other stars that are Earth-sized, Venus is still the planet most like the Earth. We have yet to find one more similar to the Earth than Venus. Next, please. And this just documents this finding. These are from various observing campaigns for exoplanets. Some are confirmed and some are still waiting to be confirmed. But in terms of their insolation coming in, the vast majority of these Earth-sized exoplanets are in fact in the Venus zone, as opposed to the present-day habitable zone of Earth, where we think that there's liquid water. Next, please. So yeah, and this is the TRAPPIST system. You're probably pretty familiar with this. The fascinating thing about all of these exoplanets that you hear about, the vast majority of them are super close to their suns. In part, it's an observational bias, but it's also just a difference so far in the solar systems we've seen. And this TRAPPIST system all fits well within the orbit of Mercury. So these planets are very, very close to their sun, which is much, much more faint than our own sun. So when we think about Earth, like really when it say a planet is really what that typically means that liquid water may be stable. So and that it's a similar size, perhaps a similar bulk density. But we have a long way to go to really being able to say that any of these exoplanets are Earth-like in the sense of for sure having liquid water or any hope of harboring life. Next, please. But that doesn't stop artists from creating possible views of what these exoplanets might look like. If you're, I hope, okay, they were seeing that slide. Yeah, so this is a possible rendition of what the surface of TRAPPIST-1e might look like, and it's definitely fun to imagine what these planets may look like. Next, please. And of course, what we can do is get the density. The size of these is estimated from their transit effect, and the wobble of their orbits is a means to estimate the density. So we get the density of these exoplanets, and can create some different scenarios of what the structure of these planets may look like. Perhaps they have no core, maybe they have a mantle plus a core. It could be the ocean mantle and large core, as portrayed in the previous artist concept of having a significant ocean at the surface. And that's possible for the outer TRAPPIST planets, but the inner TRAPPIST planets are just too hot to have liquid water at the surface from everything we estimate of what's going on there. Next, please. So what about Venus? What about its habitability over time? If you go to the next one. So one thing to remember is that the suns evolve with time. They become more luminous over time. And in this is our current our current habitable zone. However, even though Venus is far from habitable today, in the past it may have been much more habitable. Go to the next slide, please. So this shows the history of our solar system with the various rocky or terrestrial bodies. And orange is the volcanic and tectonic activity that's thought to be necessary at the surface to create chemical disequilibria to support life, as well as the presence of liquid water on the surface. So you can see that the bar for Venus's liquid water starts earlier than for Earth. And that's, of course, inferred from the possible history of the sun and the estimates of temperature at the surface. We think that there's still ongoing activity. We don't really know when Venus lost its surface water. That could have been as recently as 1 billion years ago, but that's not well determined. And Mars, of course, we know had liquid water for a pretty limited time early in its history, and there's still a tiny bit of activity on Mars due to cooling, but Mercury and the Moon, never got there as far as we know in terms of having habitable conditions. Next, please. So you may have heard about the phosphine controversy. Whether or not it was there are two controversies. One, was it actually detected? And two, what does it mean? So some authors who wrote this paper, I guess about 6 months ago, advocated for seeing this molecule in the clouds of Venus from Earth-based observations. However, That's been challenged as to whether that was a valid observation or not. And the interpretation that it could have only come from bacteria giving off those molecules has been challenged. It's possible that volcanic activity could have brought these molecules up from the interior of the planet. It's not known if the chemistry in the interior is viable, or if they're being, or if it could be released volcanically. But it's a very intriguing idea, of course. It would be, an amazing discovery if, in fact, these molecules are a result of life, and if they can be confirmed in the atmosphere of Venus. But for now, as Carl Sagan said, extraordinary claims require extraordinary proof. So we'll see what happens. Okay, next, please. So really, in terms of habitable planets, my interest and that of many other people is the divergence of Earth and Venus. Earth is the only planet with confirmed life. What are the conditions, especially conditions as viewed from the perspective of an exoplanet, that allow Earth to become and remain habitable? We think that, so this is Venus in the bottom and Earth in the top. We think that they evolved quite similarly up to a point. At some point, Venus lost its oceans, and Earth retained them. So, the simple answer is that Venus is closer to the sun and it lost its ocean as the atmosphere heated up. But it's a lot more complicated than that in terms of how the atmosphere formed, how it's affected by surface geology, volcanism, and perhaps subduction on the Earth. Subduction, which I'll talk about in a bit, takes volatiles back into the interior of the planet as slabs of the outer lithosphere, the strong part of the crust, sink into the mantle, effectively sequestering the carbon dioxide from the seafloor into the mantle, which has a huge effect on Earth's climate on the long term, on the hundreds of millions of years time frame. So next, please. So I like this perspective on the rocky bodies, the solid bodies in our solar system. We're all used to seeing those globes, but this really makes the point of what an important body Earth is in our solar system, and what a great accident it is that we have these two bodies that are so similar in their surface area, their size, and that is important for understanding the evolution of the Earth. It basically gives us this great control case to begin to understand the conditions that have been important for the Earth and evolving to its present day state. So if we go to the next one, please. The size, of course, translates into interior pressure and temperature. And, we've learned a lot of things from each of these planets, but the moon actually, we do know, has a core. This is an old slide. I meant to cover that up. But, for Venus, we have just gotten in the last few months the first kind of crude idea of the size of the core. But, much of what we know about the early formation of the crust, the mantle, and the outer shell, the outer compositionally buoyant crust, is from what we have learned about the interior of the moon from seismometers that the astronauts deployed. So planets form in a molten state as the planetesimals come together and create so much heat and energy as they crash into each other. And very rapidly in the formation of a planet, you get the separation into layers of the core, mantle, and crust. The moon, of course, has that beautiful light material at the top, at the crust, predominantly this crust made out of feldspar that's very bright and reflective. And that formed because of the particular pressure and temperature conditions when the moon was molten and beginning to separate into different layers. Now, the pressure inside the moon is equivalent to, a few hundred kilometers under the surface of the Earth. And the pressure in the interior of Mars is actually, equivalent to less than 1,000 kilometers into the interior of the Earth. So, understanding how these bodies have formed and evolved has particular lessons. And in fact, it was great to understand what the size of the Earth, of the moon's core was, the thickness of the layers, because well, the moon in particular and Mars to a large degree, the core formed very early on. And the crust formed very early on, and because of a lack of subsequent geologic activity, that initially formed crust is still preserved. On the Earth, that crust is essentially gone because of plate tectonics. And on Venus, we know that the surface is also young. So, we learn about something from each planet. From Moon and Mars, we can learn about the initial formation processes of planets. And from Venus, we can try to understand the puzzle of why these two planets that are very similar in their initial conditions have evolved to such a different states. Next, please. And as we've been trying to, as the broader communities have been trying to understand how to predict whether a exoplanet is in fact habitable or not, we've come to appreciate more and more the role that the geodynamics plays for a planet. And geodynamics is essentially the links between the interior convecting part of the mantle and even the core, and how that links to the surface geology and formation of the atmosphere and hydrosphere. So, all of these factors are really important for determining, when a planet becomes habitable, how long it maintains habitability. And, we've just been seeing more and more links between these big scale processes on the Earth and its habitability over time. So next, please. So, in the exoplanet community, they've identified a number of factors which are believed to affect habitability. You want to have water at the surface. You want to have a secondary atmosphere. There's an atmosphere that forms right after or during the differentiation into the various density layers, core, mantle, and crust. But that is mostly blown off by early impacts. And so the atmosphere that planets in our solar system have today are a result of their volcanic history. Water and other gases being released from the interior of the planet via volcanism. You also want to have that volcanic and tectonic activity, as well as the processes where rocks are interacting with the atmosphere and chemically modifying. So, without that ongoing activity, not only can you may lose your atmosphere over time, but also you want to have these kind of ongoing geologic processes to create chemical disequilibria, which life really likes. You want to have a big internal energy budget. Essentially, the Moon, Mars, Mercury are, they stopped being significantly geologically active long ago. And that's because of their size, essentially. The radiogenic elements, uranium, thorium, potassium, these elements decay over time. And that larger size of Venus and Earth have kept the interiors hot over all this time period. So we still have volcanism at the surface, certainly on the Earth, we think on Venus as well. So you need to have a robust energy budget to keep a planet habitable. And a magnetic field is known to shield the surface from radiation. So all of these things are found they either were on Venus in the past. For example, these tessera that I'll talk about, we think are evidence of past water at or near the surface. And I'll talk about evidence for all these other things as I go along. Next, please. So, one thing I'm super excited about for Venus in terms of their uh, what we hope to find out is the fact that Venus has these orange features there, those tall plateaus. We have reason to think that they are analogs of Earth's continents. Those on Earth, continents formed initially billions of years ago, and they formed when the iron-rich basaltic oceanic crust melted in the presence of a significant water. So in that melting process, you end up extracting some of the iron, and the composition has more silica and is less dense. So we ended up with these less dense continents. These high plateaus on Venus may be analogs of those continents. And if so, they provide us with evidence of the past surface water, the chemical evidence of that past surface water. So that's a very big question that new missions are poised to answer. We also, have reason to think there's subduction on Venus. That's the process where one of the, on Earth we have plate tectonics, where the plates, the strong outer part of the planet, the lithosphere, is broken into plates that move past each other. Subduction is when a strong plate sinks into the mantle. And we think that process may be occurring on Venus today, that kind of almost circular feature that you see underneath the orange one on the right. I think that's a subduction zone. I'll talk more about that. I'll just go through and talk about some of these properties that Venus either has today or we think had in the past, and how studying these features on Venus may help us understand rocky planet habitability overall, and help us as we try to seek an exoplanet that's Earth-like, how we can try to model these processes from a few inputs that we will ever be able to get for exoplanets. Next, please. Okay, so this gives a little cartoon of plate tectonics. Perhaps you're all familiar with this, but the plates have different types of boundaries. New plates form at the mid-ocean ridges, where hot material wells up and creates the oceanic crust constantly. And then most of the subduction zones are continental or oceanic crust sliding underneath the continental crust. And when those subducting plates melt, you get volcanism. You get those string of gorgeous volcanoes starting around Mount Lassen and going up through Rainier and Mount St. Helens and so forth. So the plate tectonics is effectively Earth's geodynamic regime. And early in the exploration of Venus, people expected it to have plate tectonics like the Earth. With the data that we have currently, it appears that it does not, but it may be early in the process of developing plate tectonics. I'll talk about that in a second. Next, please. So the study of plate tectonics is about 50 years old. And a big question in the study of plate tectonics today is, how did it start? There are a lot of different theories of how it may have started. Going back in time to the first billion years or so, plate tectonics was not present, continents were not present, and the lithosphere was still quite hot. That hot lithosphere that's present in all planets is also found on Venus today due to its massive greenhouse atmosphere. So the conditions that we see on Venus today may be quite analogous to those of early Earth, where you have just kind of maybe the start of subduction, you have the start of continent formation, and you still have this hot lithosphere. So it kind of gives us a laboratory to begin to unravel how Earth got its start down the particular geodynamic regime of plate tectonics. Next, please. So as I mentioned, people have been investigating how plate tectonics and formation of continents and so forth may have influenced the development of life on Earth, as well as the ongoing climate, the variations in climate. And this is a speculative idea, but it's very interesting in that on the left we see a diagram of the key elements that are essential for the formation of life and their cycle in terms of once continents are formed, water erosion carries elements from the continental crust into the ocean. The elements that are linked to life, carbon, phosphorus, these nitrogen, all those elements are more abundant in continental crust than they are in oceanic crust. And so all of these elements getting enriched in the ocean may have been the reason for the great oxygenation event in which life really began to take off in a huge way in the oceans. So possibly we have formation of continents along with formation of subduction zones to thank for this outburst of life on the planet. Next, please. So, planets, life at the surface is happier when it has a nice magnetic field to shield it from incoming radiation. And, like plate tectonics, we expected that Venus would have a dynamo. Some people have proposed that the reason it doesn't have a dynamo is because you need to have a convecting core. In order to have a convecting core, you need to have heat being transported from the core across the mantle and to the surface. And on the Earth, plate tectonics is a super efficient way for the planet to lose heat. So people have said, well, Venus doesn't have plate tectonics, therefore there's not enough heat coming out of the interior to drive a dynamo. So that's a good hypothesis. However, not security, which definitely does not have time, and it has a dynamo. So, the more dynamos we discover, the more strange and unpredictable we see that the dynamo history is. So, possibly Venus had a dynamo in the past, but no. Hi, I think my phone spaced out there for a minute. Can you still hear me?
We can now. Thank you.
Oh, okay, great. Okay, next, please. So in this slide, you see two subduction zones, or in the upper left. One is on the Earth and one is on Venus. And these are the same horizontal and vertical scale. So the one on the right is that one I was pointing out in the global view, and on the left is the Aleutian Trench off of Alaska. So you can see that they have a number of similarities, but the cartoon there shows the hypothesis put forward fairly recently for this feature on the Earth, because on Venus. So the hypothesis is that this feature formed via plume-induced subduction, where hot mantle material comes up and pushes the topography up, pushes the surface up, creating a topographic bulge. That bulge allows the center to fracture as the lithosphere is stretched, and the massive amounts of volcanism that escape create a load in the surface. and that load pushes the flap of the lithosphere downward. So, this has been a controversy for decades on Venus. Are these features that are, quasi-circular, are they due to mantle plumes because of their shape, because of the presence of volcanism, or are they subduction zones because of the deformation that's observed and the nature of the trench and so forth? And so this hypothesis of plume-induced subduction was first suggested for the Earth as a way to get plate tectonics going. You have to break the lithosphere to get plate tectonics going. And so it was proposed that this combination of a plume initially breaking the lithosphere, volcanic loading, and then the sinking of the lithosphere could be a way to get plate tectonics started. And this feature that there's a number of features like this on Venus, but this particular one we're looking at, it really fits this model and this hypothesis very well. So, we were able to observe on Venus this process that could have happened early on in Earth's history. Next, please. And I also talked about the need to have activity on the surface. On the left are diagrams of the number of impact craters on Mars and Venus. On Mars, there are hundreds of thousands. Venus, only about 1,000. Of course, the dense atmosphere of Venus does filter out craters less than about 10 kilometers, but still there's only, there's many fewer impacts of the same size, 10 kilometers and up. So, it clearly has quite a young surface. And there's also been evidence for recent volcanism from a European mission that ended about 6 or 7 years ago. Basically, in the middle there, you see some flows on Hawaii. Those silver ones just formed a crust over the incandescent lava, minutes before I took this picture. And within hours, it looks like the normal black basalt that you think of for Hawaii. And, it basically what's happening is that when that lava is erupted on the surface, it's out of equilibrium chemically with the atmosphere. And so you get a very slight change in the composition due to that chemical weathering that occurs super rapidly in the Earth. The bottom right feature shows, a feature on Venus. That orange color there is evidence of the iron mineralogy from surface emissivity. And that is consistent with those flows in the top of this volcano being relatively fresh basalt. And they're apparently chemically unweathered. We don't know how long weathering takes on Venus and exactly what the chemical interaction is, but there are, 6 or 10, say, volcanic areas where we believe the volcanism is quite recent. Now, not all the surface has been covered, and the data is not as precise as we'd like it to be, but it does provide good evidence of recent volcanism on Venus. And we hope to be able to in future missions see active volcanism. That's the current volcanic eruption seen in Iceland at the cloud level. The incandescent glow is basically being reflected off the clouds. And that's what you would see from a spacecraft in orbit above Venus if there were active flows in the surface. Next, please. Okay, so one thing that has really changed in the last perhaps decade is our understanding of where do volatiles come from on planets. Where's the water come from? It used to be thought that comets were the primary mechanism for delivering water and other volatile gases to the surface of planets. From the chemical measurements of comets, as well as a number of different classes of asteroids, of chondrites, what we've learned is that, in fact, comets are contributing only a small fraction of the volatiles on Earth, and the building blocks of planets, these carbonaceous and other types of chondrites, basically equivalents of planetesimals, of the small bits of stuff floating around that form planets, they actually have plenty of water in the interior. So so basically that's this idea that I talked about earlier in terms of you need to have the volcanism to create this secondary atmosphere. You need to have a way to bring the gases from deep inside a planet to the surface and create that atmosphere and hydrosphere that gets preserved at the surface. For Venus, that's extremely important. I mean, for any planets, it's important, but for understanding the difference between the Venus and Earth, it's super important because people used to think, oh, Venus's atmosphere is dry, not much water, therefore the interior must be dry. And that's why it went down a different evolutionary path from the Earth. But the limited isotope data that we have for Venus suggests that, in fact, there may be more water in the interior of Venus, perhaps because the lack of plate tectonics has made the efficiency of bringing stuff from the interior to the surface lower than that on the Earth. But we really want to have better measurements of the isotopes to truly verify that. Next, please. So that's the majority of what I wanted to say about habitability. I wanted to, if you've been following the news about NASA, we've just completed the hat trick where we have 3 new missions selected for Venus. We have the 2 missions from NASA on the right, VERITAS, which is going to be an orbiter, and Da Vinci, which is going to be an atmospheric probe. And the European Space Agency almost simultaneously long day, selected a orbiter to go to Venus as well. So we're calling this the Decade of Venus. And the Venus community is just extremely thrilled to be finally having missions planned to get back to Venus and start to answer many of these questions. Next, please. So I'm the principal investigator for VERITAS. So I'm just excited to tell you a little bit about this mission. This is our cover art. Next, please. And the mission is intended to address many of these key questions about the evolution of Venus. Does it have these continents? What's the volcanic history been? Is it catastrophic? As probably if you've read any textbook or paper about Venus, say it resurfaced 500 million years ago. Well, I honestly don't believe that's true. I think it has continued to resurface over time, not in one big catastrophic event, but with this mission, we'll be able to determine for sure what the volcanic history has been. And we'll study these features that appear to be subduction. Is it active today? And what are the conditions that are allowing that process to occur? And we're also going to look at, how thick is that lithosphere? How much heat is flowing across the lithosphere from the interior to the surface? Next, please. So we have just a couple of instruments and a radio science experiment on this mission, but each is going to provide different types of data and answer different questions, multiple questions. So with our radar instrument, we'll create a global map of the topography at 250 meter horizontal resolution, 5 meter vertical. The global SAR imaging, radar imaging, is 30 meters. Of course, we have to look through the clouds, so we can't get visual images from the orbit. And we'll take higher resolution images, 15 meter resolution over a quarter of the planet. We'll also make the first interferometric deformation map. So if you've seen those quake maps of where the surface of the Earth has moved relative to previous radar images, we'll be able to make those kind of maps in certain locations for Venus, and we'll be able to compare our data set to that was acquired 30 years ago from the last mission from NASA to Venus. We have a spectrometer that is especially designed for Venus. It was thought that it was impossible to do spectroscopy on Venus because of the thick clouds, but we've designed this spectrometer based on the limited data from the European mission Venus Express, which was able to see through some of the clouds at around 1 micron. So we'll be able to see the surface in 6 bands and be able to answer some important questions about the iron composition, the rock types. As I said, we want to be able to tell continental rock, the so-called felsic rock, versus the more iron-rich, oceanic, if you will, basaltic crust, mafic, and we'll search for volcanic activity. And with the gravity investigation, we'll be able to tell a lot about the density structure inside the planet and get the first really meaningful estimates of the core size, which will tell us the state. And from getting the size, we can learn more about the composition, which will help us better understand this mystery of why no dynamo. Next, please. So this is an example of the kind of topographic data that we have currently for Venus. And if you could hit advance, please. This is the resolution of the data that we'll get for the topography using, Hawaii as an example. So the resolution of the topography will be 100 times better than we have currently. The imaging will be 10 times better, and the gravity field will be a factor of several higher. And that's very important for certain types of investigations. Also to make the first global maps of rock type and be able to look at the weathering of rocks and do these first surface deformation measurements, as well as really get at active and recent volcanism, as well as look for water being outgassed from the interior. Next, please. So this is just shows a little bit more about this process of looking for surface rock types. You may have seen those images from the surface of Venus, taken by Soviet landers many decades ago. The middle orange slice there is a radar image, colorized, of course, but that really crunched up material there is one of these features that we think is possibly low density, low iron crust. It's all rough. That's why it's so bright in the radar. And, maybe a Joshua tree, which is also granitic in its composition and has been crunched many times, is a good analog for what we're seeing on Venus. But we need to get the chemical composition to really be clear about that. Next, please. And as I said, we're going to be looking for water coming out of the interior of the planet. There have been SO2 variations observed in the atmosphere of Venus, which may be due to ongoing volcanism, but we'd really love to be able to look for water, because that will tell us what's going on inside the planet. Has it really retained a lot of water, or has it been lost completely? Next, please. We'll also answer this question of whether there was this huge volcanic event that wiped out all the previous impact craters, or if there's been volcanism going on over time. It's a really important question, not only from the habitability standpoint, but from understanding what's going on inside the planet. Is it Earth-like, or is it some weird thing? And last, please. This is a picture of Venus I took from near my house the night before we found out the mission was selected. So it seems like a good omen. All right, thank you. That's my talk.
Thank you very much, and congratulations on being named the principal investigator for VERITAS. That must be quite a professional challenge and reward.
Yeah. I've been working to get this mission selected for over a decade. So it's been a long process, long time coming. A lot of us are working on it. It's a big team, and I've proposed it. This is the 3rd time. So the 3rd time was in fact the charm.
Well, congratulations. I can ask questions all night, but let's see if anyone else has any questions.
Yeah,
AC?
hi, this is,
Oh, sorry, Raymond.
okay. How big a difference between Earth and Venus is governed by the fact that Earth has a relatively large moon and Venus has no satellites at all?
Yeah, that's been an ongoing question. And unfortunately, there's not really a good way to test various hypotheses. I mean, people have suggested that, maybe Venus had a major impact early in its history, right? Because it, rotates very slowly and, it does have some differences from the Earth. But, that could have happened. It could have, dried out the interior. That's a hypothesis. But at this point, we don't have any data to test that hypothesis. We should be able to get hopefully some constraint on that from the Da Vinci mission, which will be taking a variety of isotopic data, noble gases in particular. And it's possible that they'll get enough data to try to test that hypothesis. But right now, it's an interesting idea that we can't rule out or confirm.
Next question.
I have a question from the chat. AC would ask, and let's see if I even understand the question or can read it. If there is an atmospheric 1 micron window, why not use an appropriate laser altimeter for this particular wavelength?
Yeah, laser altimeters can't penetrate at that wavelength.
Ah.
Yeah. But our spectrometer can, and it's confirmed that there is this window at 1 micron based on data from the Venus Express mission from ESA.
And there's another question on the chat from Clarence Bodner. Is there LIDAR data available to the public of the surface features on Venus?
There is topography data, yes, through which was obtained from a past radar mission. Yeah, so if you search Magellan topography Venus, you can find that data. It's available on various websites.
Okay, AC asked, I wish you'd ask it yourself, AC. Could you also expand on the lack of geomagnetism in Venus?
Yeah, so, we know, on Mars, for example, we know that it had a dynamo early in its history. And we know that based on detection of the magnetic field due to crustal magnetization. So, when rocks cool in the presence of rocks with enough iron, when they cool in the presence of a magnetic field, the minerals line up and they generate their own magnetization. So certain rocks, not all, but like hematite, magnetite, minerals with plenty of iron will align within the cooling rock and create so-called crustal magnetization, remnant magnetization. So we know that Mars at one point had a dynamo. Now, the problem with the crustal remnant magnetization for Venus is that these rocks, if you heat them up high enough to a high enough temperature, they'll lose that magnetization. They can't retain that orientation of those minerals. But there are a few minerals which we think which have been shown to maintain their magnetization even at the temperatures of Venus. The question is, are there large enough concentrations and thicknesses of them to be observed? So, there have been some measurements of Venus and not enough to rule out the possibility that there could have been one in the past, or that there might be an extremely low level magnetic field. But why is there no dynamo today? Why is there no big robust one like on the Earth? Honestly, it's still a mystery. I think that we still don't even know the actual size of the cores. We don't know its composition. And it's just a puzzle.
Let
But
me
people want to send magnetometers to the surface and see if we can see evidence of a past one. We'll see.
let me ask a question for my question. If we're looking for life on exoplanets or other planets, and I would guess Venus is not the best of places to go looking, do you think that we can detect life with any degree of certainty based on chemical signatures from spectroscopy, or do we have to visit the planet and get some sort of fossilized remnant of life?
Well, you know, it's interesting because how to detect life depends on what you're studying, apparently, because you know, if you for exoplanets, you know, they have missions called Life Finder, or concepts called Life Finder and things like that, and basically they're looking for planets that are similar in size to the Earth and you know, have evidence of water at the surface. So, you know, that's a start, right? But you know, obviously we're never going to learn enough about an exoplanet to be 100% definitive, in my opinion. You know, and people that are studying Mars, they say, okay, we got to bring a sample back. You know, we can't tell you if there's past life unless we bring a sample back. Others who are studying, you know, Europa and so forth, they, you know, want to go to the surface, but, you know, I think it's going to be hard to say just based on a chemical observation that life definitely exists. In my opinion, it's not my field. I'm not an astrobiologist, but you know, again, you need extraordinary proof, and it's going to be hard to get it, in my opinion, just based on the chemical signature. But you know, think about the asteroid ALH 84001, right, where they thought they found fossils in an asteroid from Mars, and you know, eventually that fell out of favor. But as a result, we learned so much about extreme environments on the Earth. People were scrambling all over strange, bizarre environments on the surface of the Earth, and learned so much about the fact that life is present every damn place we look on Earth. You know, so you know, similarly with this phosphine. Will we prove that there's life on Venus? You know, I'm guessing no. But you know, we can learn more about what it takes to produce phosphine. We can learn more about the trace gases in the environment of Venus. And you know, I think these things ultimately lead to good science, whether or not they lead to life.
Thank you. We have a question on the chat. Did the smaller gravitational force on Venus play some force in the composition of the atmosphere today? For example, Mars had an atmosphere, but it had lower gravity, which made it lose it. So are there, I'm not sure exactly what he's asking, maybe you do.
Well, you know, for a long time, we thought that the major factors in a planet retaining its atmosphere were gravity and the presence of a magnetic field. So the gravity just, you know, wants to hang on to those molecules, and the magnetic field helps shield the upper atmosphere from solar particles. But in the last several years, missions to Venus, to Mars, have found that the rate of escape of oxygen from Earth, Venus, and Mars are about the same.
Oh.
So what's up with that? You know, it's very surprising. And so again, we don't fully understand how planets hang on to their atmospheres. You know, it was thought, as you said, that because Mars is small, it lost its atmosphere, and you know, with Venus, it's slightly smaller, but the atmosphere is actually much more dense than that of the Earth. So, yeah, we're still trying to figure that out.
One of the missions that you described was going to send an atmospheric probe.
Mm-hmm.
How long do you think it will last?
Oh, yeah. I mean, the descent through the atmosphere is about an hour. You know, it's kind of like the atmosphere is so dense, it's kind of like falling through water. So yeah, there's not much they can do to make it anything other than about an hour in terms of the descent time. And for that particular probe, I doubt it will last at all for any length of time on the surface. You know, maybe minutes, but probably not an hour.
When we think of Venus, we tend to think of, with sulfur dioxide and water and so forth, we think of raining sulfuric acid.
Right.
Is that a good characterization?
Yeah, certainly sulfuric acid rains. It doesn't make it to the surface, probably. It's probably too hot. It probably evaporates before it actually makes it to the surface. But yeah, it does have sulfuric acid rain. It's very picturesque.
Are there more questions from the group? Well, I'm sorry if I monopolized all the questions. I have to thank you for this great presentation. This is not something that we normally think about for an astronomy club, but it's
Sure.
fascinating. So thank you very much for being willing to make the presentation.
My pleasure. It's always fun.
Okay, thank you.
Right.
Please
All
come
right.
again, and hopefully you can make it to some of our events. And we're all hoping that Palomar Observatory will open for tours in the near future.
Yeah.
It still
Yeah.
seems to be in doubt.
Well, I hope so too. All right. Have a good evening.
Good
Good
evening.
night.
Thank you again.
Thank you.
Okay, and I did miss one question in the chat that I didn't ask. Thank you everyone for participating. We will continue to have a lively set of program meetings via Zoom, and we'll probably recommence live with also an ancillary Zoom when we get back admission trails, whenever that might be. It's still up in doubt. The city seems very reluctant to open the facilities and the libraries and everything else. Next month, we are trying to stage a live meeting with an actual astronaut. So everybody think of your astronaut type questions, please, not how to go to the bathroom in space, but other things that are very practical. So with that, let me close the meeting. Are there any final comments from the group?
Sorry, I didn't notice I was muted. Excuse me. As I was saying, the ASIC meeting will be next week, and unfortunately, I'm going to be gone. Bill Jacobs, one of our members, is going to give us a talk on imaging, and it's really his talk is really aimed at the beginners in this area. And so I'm hoping that we get some new people come to the ASIC meeting and get to hear how to get started in astro imaging. And as I say, I won't be around, but Dave Wood's going to take control here, right, Dave?
Well, I've been around on most of the meetings anyway.
Yeah, right. So that's the schedule for next Wednesday. And then in July, what I hope to do is to use one of the tarot images. We have taken many very excellent deep space images with tarot. And I'd like to get the group to do on maybe the same or one or two specific images, get the group to do analysis and produce a very pretty picture. And we'll compare them and see how different people approach image processing. That's for July, not this month. So that's what I know about ASIC.
Okay, and everyone, please stay tuned to the online calendar and the groups.io for changes in the schedule, because hopefully this whole COVID reopening has been very dynamic. And hopefully the city will make some kind of movement and begin to open things up in July. Hopefully July, I would guess October for sure. But we may be back at Mission Trails, or we may be back in the campground in West Sycamore by then also. So keep your telescopes dusted.